Cool. So because it's a long topic, it's really just one really long chapter. I know it's broken down into different chapters in the textbook and the syllabus, but really it's just organic chemistry. So just to quickly remind ourselves where we are, we did most of the basic skills. That's what we did in class with those tables that I gave you, where we converted between structural formula, molecular formula, skeletal formula, all that sort of stuff. What we're busy with now is the chemical changes, so the functional group conversions. And we're almost done. I think we've got about 2 or 3 more to go. So we've just got the carbonyls left. And then I think the last topic is esters, carboxylic acids and esters. And then we're basically done. And then Kamaz, you were asking about nucleophiles and electrophiles. That comes here under mechanisms. So when we learn about the process of how one functional group gets converted to another functional group, we'll talk about what's called the mechanism. And in that case, we'll use the word nucleophile, electrophile, and all that sort of vocabulary over there. Well, and then the last topic, it's kind of actually the same as chemical changes, and it's chemical testing. And the reason why it's the same as chemical changes is because we know that certain functional groups have certain predictable patterns of behavior. And because we know there's certain patterns of behavior, we can use that to test for them. So you'll see that the tests for the functional groups are actually themselves probably functional group conversions. Ooh, and if you notice a change in the chemical structure, you know that that functional group is present. Ooh, so those two will tie nicely in together. And there's not that many chemical testings. I think it's testing for primary, secondary alcohols, and then it's testing for ketones, aldehydes, and carboxylic acids. Cool, so that's basically where we are. Cool. Any questions based on what I just said? No, we're doing good. Yeah, we're doing very good. We're almost done with the functional group conversions. Mechanisms is about 3 or 4 mechanisms, and then chemical tests is about 3 or 4. So we're doing very well. We're on track to get everything done on time. Okay, so just to remind you where we are, we spoke about alcohols, we talked about the oxidation, we talked about the reduction. We talked about the addition to sodium metal to form the ethoxide, etc. The last thing we just have to talk about is the dehydration. And the dehydration of the alcohol is exactly the same as what we did with the halogen-alkanes, where we eliminated the halogen-alkane to form the double bond. So it's exactly the same concept. And you'll kind of notice that this reaction is almost exactly the reverse of the reaction that we've seen before. So if you take ethene and if you add water, you're going to form the alcohol, but we can also do the forward reaction, which is the elimination. It's not a reversible reaction, so it's not going to be forming in an equilibrium or anything like that. You can either do the elimination or you can do the addition. It doesn't happen simultaneously. It's not happening under equilibrium conditions. Cool. The only specific thing here is that you have to add a catalyst. So the most important thing is to remember is that you have to add, it's quite a high temperature, so 170 to 180 degrees Celsius. And then you have an option of 3 different catalysts. So you don't add all 3 catalysts. You have an option of aluminium oxide, concentrated sulfuric acid, or concentrated phosphoric acid. So those are the 3 catalysts that you can add. Remember that a catalyst is something that speeds up a reaction. It doesn't take part in the reaction itself. So in other words, the HPO3 or the H2SO4 is not going to add or subtract from the molecule. It's just going to help remove the water. Cool. And then the way that they've drawn this one was quite nice. You can see here that these H's and these O's become the H2O. And then what happens is you form the double bond. So you'll see here that a double bond is formed between that carbon and that carbon. And then you add another H over here where the oxygen is left. Cool. So that would just be the dehydration. So when you say dehydration, it almost sounds exactly what it sounds like. You're taking away water, you're dehydrating something. Cool. So you're removing water. Any questions? You good? Good. And this can happen with anything, primary, secondary, or tertiary. So you can look at a couple of examples. Here's the dehydration of propan-1-ol. So if you look at propan-1-ol, it's the primary because it's on the last carbon over there. And you're going to form the double bond over there. So what's happening here is that you're getting rid of this OH group. Let me see if I can draw this with a scribble. Yeah, you're getting rid of that, gone, 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 gone. And then you're forming the double bond over there. Cool. So you're removing the OH and then you're reforming the double bond. And then, so this here on the bottom is the one propanol that we started with. Cool. So you're going to get rid of this, get rid of that, get rid of this, get rid of that, get rid of a hydrogen over here and form the double bond over there. Hang on, that's the wrong way around. Undo, undo. Don't get rid of that hydrogen, get rid of that hydrogen and form the double bond there. And then you'll see that that's the propene molecule that forms over here. So you have the CH3 on this side over here, you have the CH over here, and you have the CH2 over there. Cool, everyone happy with that?
Mm-hmm.
Good, good,
Yes,
good.
sir.
And then interestingly enough, if you take the propan 2-ol, which is the positional isomer, this is the secondary alcohol. So you'll notice that the oxygen is on the middle carbon. You're going to get exactly the same product. And the reason is because you're going to eliminate the OH with one of the hydrogens and you're just going to form the double bond. So whether you form the double bond on the left or the right is irrelevant because it's the same product, just mirror imaged of each other. So in other words, this, if I drew like that, is exactly the same thing. I've just flipped it horizontally. Cool. So the double bond could form on the left or on the right. It makes no difference. So if you were going to do that, you could think, scratch away the OH, get rid of that, get rid of a hydrogen on the next carbon. So you get rid of one of those and you form the double bond over there. Cool, but that's not the one that you see on the right-hand side. The one that you see on the right-hand side, if you did it this way, would look like that. Yeah. So you've got the double bond on the left and the single bond on the right. But you could have easily have done the opposite and you could have eliminated the other hydrogen. So you could have done this, got rid of you, and formed the double bond there. And now it makes sense because it's in the same order. So just to highlight, in case anybody at home has any questions or anyone on YouTube, you can see that this here is the CH3. So that's the CH3 over there. This middle carbon is the CH. That's this one over here. And then the CH2 is what you have on the right-hand side. That's this carbon on the far right over there. So you've just gotten rid of the OH and you've gotten rid of a H on the adjacent or the next door carbon. Cool, any questions? Nope. Good, good, good. So exactly the same if you have a look at, halogen alkanes, it's exactly the same as if we were eliminating a halogen alkane. So something like this, for example, same sort of concept. You get rid of the Br in this case, and you form the double bond. And in this case, it's obviously not dehydration because you're not getting rid of water, but it's the same concept. You're reforming the double bond. Cool. And then if you think back to your functional
So is this like hydrolysis?
It is sort of like hydrolysis, but it's not, because you're not breaking a bond by adding water. What you're doing is you're removing the water.
I mean condensation. Sorry, condensation.
It's similar to condensation, correct? So you can think of it like condensation because you're removing water from the molecule 100%. So it's very similar to condensation. Cool. So it's dehydration in this terms because we're dehydrating the water, we're taking it away. But condensation would be a synonym in that case. You're absolutely correct. Cool. Hang on, not that one, that one, that one, that one. Okay, so if you have a look over here, you can see on this, we can go from alcohols back to alkenes. Cool. And they've suggested the hot pumice with aluminium oxide. They've told you use aluminium oxide, but you can use the hot concentrated phosphoric acid or you can use the hot concentrated sulfuric acid. Either one would work. Cool. So you can do that conversion there now. Cool. If there's no more questions, then we can move on to the carbonyls. We can move on to the aldehydes and the ketones. Good. Cool. Then we'll go on to carbonyls. So I'm not going to spend too much time on this because in reality, it's actually just the reverse of the oxidation. So what you can do to the alcohol to form the carbonyl, you can do exactly the reverse process and you can reverse it. So you can undo the oxidation by doing a reduction. Cool. So formation of aldehydes and ketones was covered in alcohols part 2. So we don't have to talk about the formation of them again, because the formation of them, they were formed from alcohols, which we already talked about. So just as a reminder, primary alcohols will form aldehydes and secondary alcohols will form ketones. And we already said that tertiary alcohols can't do anything because they can't be further oxidized. So we can't do anything with tertiary alcohols. Also, formations of aldehydes and ketones, they come from primary and secondary alcohols. And then what we can do with them is we can reduce them. And what we need now is a reducing agent, and we call the reducing agent this square brackets with the H. Cool. So reducing agent is something that adds hydrogen or removes oxygen. And the two that we're going to use are sodium borohydride or lithium aluminium hydride. There's other reducing agents, obviously. I mean, there's probably thousands, but these are the two that we're going to focus on. And then what you'll notice here is that we take the aldehyde, in this case, and we turn it into a primary alcohol. And if you notice, if you do the arrow in the opposite direction, if you did this, if I did it that way, this would literally be the opposite, and this would be the oxidation. So if you did that, oopsie, why is that not? Oxidation. But it's not a reversible reaction. It's not happening simultaneously backwards and forward. It's either you first oxidize it, take it out, and then put it back and then reduce it. So it's not forming equilibrium. Any questions?
No.
You good? So pretty straightforward. If you can oxidize the alcohol to form the aldehyde, it means you can take the aldehyde and you can reduce it to form the primary alcohol. And the position won't change either. It's going to form in exactly the same position that it started in. Cool. So it's a forward, and again, it's not reversible. We're not saying that this forms an equilibrium. Cool. And then you can have an example of propan-1-ol or propanel, Al. Al is the aldehyde, and then reduce that to propan-1-ol. So here's your aldehyde on the left, here's your primary alcohol on the right. And then what I say is look for more examples in alcohols part 2, because literally all you have to do is switch the arrow around. So if you go to alcohols part 2, that's not alcohols part 2. That's not alcohols part 2. Sorry, I'm going to get alcohols part 2, then I'll show you. Let's get drawings, and then you can have a look at these over here, and you can see that you can literally do the reverse reactions in all these cases. So if you identify this here, here's your primary alcohol, here's your aldehyde, and what you can literally do is you could take an arrow and you can point it backwards, and you can say that, well, if I can oxidize it going forward, it means that I can do exactly the opposite and I can reduce it going backwards. Cool, you happy with that? Good, 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 good. So in other words, you can have a look at all these examples here and you can literally draw an arrow going backwards.
So can you please repeat? I wasn't here.
No problem. So what I said is that to look for more examples of reduction of aldehydes, you can go to alcohols part 2. And what you'll notice is that in all these cases here, every single reaction can proceed in the opposite direction. Cool. So I can take the aldehyde and I can reduce it back to the alcohol. And I can do this for all these examples. So if I can do the forward reaction to form the aldehyde, I can do the reverse reaction to form the alcohol. I just use a reducing agent. I just use a chemical that's going to do a reduction. Cool. And if you have a look at the next example, it doesn't matter how complicated the molecule is, you can always go forwards and backwards. So if forward is oxidation, then backwards would be reduction.
Oh, okay. Thank you, sir.
No problem. So that's all we're saying. So if I can go from left to right doing an oxidation, I can go from right to left doing a reduction. Oh, and the functional group doesn't swap positions. It doesn't move from primary to secondary or to tertiary or anything. It stays exactly where it was in the first place. Cool. And then you'll see the same thing with the ketones. If you can reduce a ketone to an alcohol, you can also oxidize an alcohol to a ketone. So here's a good example. The simplest ketone is unfortunately propanone, because you can't have a ketone without 3 carbons. So if you use your imagination a little bit, if you drew 2 carbons and you put a carbonyl group on one of the carbons, it'll only ever be an aldehyde. So your smallest possible ketone is propanone. So the first example we use is propanone. Cool. So your carbonyl is in the middle, and it's surrounded by 2 separate carbons. So you know that it's a ketone in this case. And when we do the reduction, we're going to get the secondary alcohol. So it's going to be in the middle there. Cool. And then maybe Kamaz, just to go back one quickly, just to sort of think, in this case over here, you can't reduce an aldehyde and expect yourself to get a secondary alcohol, even though you would think that a secondary alcohol would be preferable. Does that make sense?
Yeah.
Yeah. So in this case, it's going to stay in the same position.
Exactly.
Yeah. So it doesn't have a choice. It doesn't have a choice to form the secondary alcohol in this case. It has to form the primary alcohol because it's on the last carbon. Cool. So even though the secondary alcohol would be more stable, it doesn't have that choice in this case. Cool. So you only get the secondary alcohols if you start with a ketone. And that's why the general conversion is when you get a ketone, you're going to get a secondary alcohol. Cool. And then basically I say the same thing again. Look to alcohols part 2, and then just read the reactions in reverse. So if we go here, and if we look at these examples, we can just, here we go. We can do all of these in reverse to get the opposite reaction. So I can go backwards and I can say that if that's an oxidation, then the bottom reaction here would be a reduction. Cool. So oxidation to the right and reduction to the left. And then I can look at exactly the same thing. I can look at all the examples and the same would be true. So if I took this ketone on the right, I could reduce it to the secondary alcohol on the left. So if I do the reduction, I'll get that product over there. And then you'll notice that the position doesn't change, obviously, because ketones always form secondary alcohols. That bond hasn't changed. Cool, I think that's the end of the lesson. Any questions?
No.
No, you're good. Okay, so I don't see you guys on Monday. So I know it's Friday, so you probably don't want to do much work this afternoon and over the weekend. But on Monday morning or Monday afternoon, when you have a bit of free time, just make sure you read through the notes and then obviously spend a little bit of time playing around with your functional group conversions. So just play around with, take a molecule, make something up, and then see what you can do with it. And then what you'll realize is that you can basically move almost everywhere around function anymore. But in any case, you can basically do all the functional conversions, group conversions on the map now. Except for 1 or 2. I think carboxylic acids is the last one, and then we're done.
And esters.
And esters, correct. And that comes with the carboxylic acids, yes. So with carboxylic acid comes esters. So we're essentially done. So if you look at this one over here, I'll just make it a little bit smaller so everything fits. We've seen all of these guys at least once by now. We've seen alkenes, we've seen halogen alkenes, we've seen alcohols, we've seen aldehydes, we've seen ketones, we've seen amines, and we've seen nitriles. So quite literally the only 2 that we have to do still are carboxylic acids and esters.
Yep.
Cool. I'll see you guys in yellow.
Exams start the week after next week, right?
I don't know. You're gonna have to wait and find out. So
I don't think we are going to write.
Yeah, I have a feeling you might not write exams, but that's not confirmed yet. So let's wait and see. Apparently, a message is getting sent out on Monday.
Okay.
Cool. I'll see you guys on Tuesday
Okay.
then.
Bye,
Okay,
sir.
sir.
Enjoy your
Bye guys.
weekend.
Be good.
So.